Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, when you think about uncovering the past on Earth, whether you are looking at like a core sample of glacial ice or the rings of an ancient bristlecone pine, there is this fundamental expectation of structural layering.
Right.
Time basically leaves a physical tactile mark.
Right.
You dig down past the topsoil, you hit a layer of limestone from the Jurassic period, and you have this, well, you have a chronological anchor. Time is buried in a specific measurable order.
Yeah, exactly. The Earth acts as a physical ledger. We rely really heavily on that spatial representation of time because it grounds our understanding of history. We intuitively grasp that deeper usually means older, and we can test the material at each stratum to build a reliable timeline of planetary evolution.
But the moment you point a telescope at the night sky, that comforting geological layer cake just, well, it completely vanishes.
It really does.
We're suddenly looking at a cosmic landscape that is, to the naked eye and even to our most powerful traditional instruments, completely temporally flat.
Right, it's completely flattened out.
You look up, and everything appears to be happening right now, all at once, projected onto the inside of a sphere.
It is the ultimate temporal illusion, really. When we observe a star field, we are bombarded by photons that left their sources at wildly different times.
Yeah.
I mean, we might see a star that just ignited a million years ago right next to a dying red giant that has been burning for 10 billion years. And to us, they are just two adjacent pinpricks of light on a flattened canvas.
Right, because we lack that physical z-axis of time.
Exactly. We don't have depth when it comes to time in the sky.
Which means, in astronomy, the absolute hardest thing to figure out isn't what an object is, but when it is.
Yes. Age is the ultimate hidden variable in space.
And without knowing the age of a celestial object, you were essentially looking at a photograph of a stranger and trying to deduce their entire life story.
Right way to put it.
Like their internal biology, their future, just from a single snapshot. You don't know the internal processes that are currently dominating their existence.
Yeah. Because age dictates nearly every physical characteristic of a celestial body. It dictates the internal structure, the temperature, the atmospheric chemistry, and, the evolutionary trajectory.
Wow.
Without an age, you cannot accurately model the physics of what you are actually looking at. You are simply cataloging static properties without understanding the dynamic timeline that produced them.
So today, we are going to explore a massive recent breakthrough where astrophysicists finally managed to crack this cosmic clock.
And it's an incredible breakthrough.
It really is. And they managed to do it on one of the most highly elusive, incredibly frustrating types of celestial objects in the universe.
Oh, absolutely frustrating.
We're going to explore the strange boundary between stars and planets. We'll learn how the physics of acoustic resonance, literally starquakes, solved a multi-decade mystery.
Which sounds like science fiction, but it's real.
Right. And we will discover how one single finding is rewriting our understanding of cosmic time and evolution. Okay, let's unpack this.
Sounds good.
Starting with the troublemakers themselves, the boundary dwellers, brown dwarfs.
Brown dwarfs. They occupy a highly ambiguous mass range. They exist in this transitional void between the heaviest gas giant planets and the latest main sequence stars.
So they're stuck in the middle.
Exactly. Generally, we classify them as objects with a mass between roughly 13 and 80 times the mass of Jupiter.
Okay, so as you know, for a celestial body to become a true star, it has to achieve hydrostatic equilibrium.
Right.
You have a collapsing cloud of molecular gas, gravity is crushing that mass inward, and the core pressure and temperature just skyrocket.
Yeah, it gets incredibly hot.
And if that object has enough mass specifically, if it crosses that threshold of about 80 Jupiter masses, the core temperature reaches millions of degrees and sustained hydrogen-1 fusion ignites.
And that is the key. That outward radiation pressure perfectly balances the inward pull of gravity.
Right, they balance out.
That sustained hydrogen fusion is the defining characteristic of a main sequence star. It provides a constant, massive internal heat source that allows the star to shine steadily for billions of years.
But a brown dwarf simply fails to reach that critical mass threshold, right?
Yeah, it just misses the mark. It forms from the same collapsing molecular clouds as stars do. It gathers mass, and its core heats up significantly under the crushing weight of its own gravity.
Because there's still a lot of mass there.
A lot of mass, yeah. But before the core can get hot enough and dense enough to ignite stable hydrogen fusion, the collapse is halted by quantum mechanics.
Wait, halted by quantum mechanics? You mean electron degeneracy pressure?
Exactly. The electrons in the core get packed so tightly together that the Pauli exclusion principle kicks in.
Right. They refuse to occupy the same quantum state.
Yes, which creates an outward physical pressure that completely halts any further gravitational collapse.
So the core becomes degenerate.
It does. It locks the brown dwarf into a state where it can never achieve the core conditions required for main sequence hydrogen fusion.
That's fascinating. So it's just stuck?
Yeah, I mean, some of the more massive brown dwarfs might briefly fuse deuterium, which is a heavier isotope of hydrogen, or even lithium.
Okay.
But those fuel sources are incredibly sparse, and they burn out very quickly in astronomical terms.
Like a flash in the pan.
Precisely. Once that initial burst is over, the brown dwarf never truly turns on.
It's essentially a cosmic engine that flooded before it could turn over.
That is a perfect analogy.
So because they lack that internal nuclear furnace to maintain a steady temperature, they spend their entire existence slowly fading. Like they are born hot from the primordial energy of their gravitational collapse, and then they spend billions of years just radiating that heat away into the vacuum of space.
Yeah, they just get colder and darker forever.
Which sounds incredibly depressing.
It's a lonely existence. But from a scientific standpoint, that continuous cooling curve is precisely what creates the massive headache for astrophysicists trying to study them.
Why is that?
Well, with a main sequence star like our sun, the sustained fusion keeps the star's luminosity and temperature relatively stable for billions of years. We can plot it on a diagram and understand its life cycle.
Oh, I see.
But a brown dwarf is constantly changing because its temperature and luminosity are always dropping. You cannot simply look at its current thermal emission and instantly know its evolutionary state.
Wait, let me push back on that logic for a second.
Sure.
If a brown dwarf is literally just radiating its initial heat over time, we have incredibly sensitive thermal cameras, right?
We do.
We use infrared observatories like JWST to measure thermal signatures across the galaxy all the time. Can't we just measure the exact infrared heat signature of the brown dwarf, calculate its physical volume, and backtrack the thermodynamics to minute 1?
It seems like we should be able to, yeah.
Like, why can't we just take its temperature and derive the age?
You could calculate the age that way, provided every single brown dwarf started its life with the exact same initial mass and the exact same reservoir of thermal energy.
And I'm guessing they don't.
They absolutely don't. And this is where that electron degeneracy pressure creates an observational nightmare.
How so?
Because a brown dwarf is supported by quantum degeneracy rather than thermal expansion. Its physical radius is largely independent of its mass.
Wait. Are you saying a lightweight brown dwarf and a massive brown dwarf are the exact same size?
Roughly the same physical volume, yes.
That is wild.
It really is counterintuitive. A brown dwarf at 15 Jupiter masses has approximately the same radius as a brown dwarf at 75 Jupiter masses.
So if I'm looking at it through a telescope, I can't tell the difference just based on size.
Exactly. So imagine you observe a brown dwarf with a measured surface temperature of 500 Kelvin. Because you can't determine its mass just by looking at its size, you are instantly faced with a paradox.
I see the problem. You just don't know the starting conditions.
Right. Is this a very lightweight, 15 Jupiter mass brown dwarf that formed relatively recently, say, a few 100 million years ago, and hasn't had much time to cool down? Or is this a massive 70 Jupiter mass brown dwarf that formed 10 billion years ago, started with a massive reservoir of thermal energy, and has been cooling down for an eternity to finally reach that same 500 Kelvin mark?
Wow. So the low-mass young object and the high-mass ancient object look identical to our photometric instrument.
They look exactly the same. That is a severe degeneracy problem.
It's an absolute catch-22.
It really is.
To understand how a brown dwarf evolves to map its specific cooling rate and figure out its mass, you absolutely need to know its precise age.
Yes.
But to determine its exact age from its current temperature, you already need to know its mass and its specific evolutionary cooling track.
Exactly. You need the age to solve the evolution, but you need the evolution to solve the age. It's an impossible loop.
That sounds incredibly frustrating for astronomers.
It is the defining frustration of substellar astrophysics. I mean, the object itself is locked in an ambiguous state. Its luminosity and temperature are changing, its radius tells you nothing about its mass, and it simply refuses to provide any independent metric that reveals its age.
So what did theorists do? Just guess.
Well, they spent decades building complex computational models predicting how these objects should cool based on various masses and atmospheric compositions.
But it couldn't prove it.
Right. They had no way to definitively calibrate those models against reality.
So because they couldn't interrogate the brown dwarf directly, astronomers realized they had to find a loophole.
Mm-hmm.
They had to stop looking at isolated brown dwarfs floating alone in the interstellar medium. They needed a twin.
Yes.
They needed a brown dwarf gravitationally tethered to something that would give up its boat certificate. And they found one in the constellation Pegasus in the HR 7672 system.
Yes, HR 7672. It is a binary system located about 58 light-years away. It consists of a primary, solar-type main sequence star and a faint substellar companion.
The brown dwarf.
Yes, a brown dwarf in orbit around it. And this specific pairing is the key to breaking the entire catch-22 of brown dwarf evolution.
Because they coalesced from the exact same collapsing molecular cloud of gas and dust.
Exactly. They share the same primordial origin. They formed at the exact same time from the same material, sharing the same initial metallicity.
Right.
Even though one gathered enough mass to ignite hydrogen fusion and become a true star, and the other stalled out as a brown dwarf, they are fundamentally siblings born in the same cosmic event.
Which means, therefore, whatever age the primary main sequence star is, the brown dwarf companion must be the exact same age.
That's the loophole.
So the star becomes the proxy. If you can date the primary star, you immediately unlock the age of the brown dwarf.
Mm-hmm.
But wait, doesn't that just move the goalposts?
Whoa.
Because main sequence stars are famously difficult to date precisely once they settle into their mature phase, right? Their surface temperatures and luminosities don't change drastically for billions of years. So how did they force the primary star to reveal its age?
This is where the methodology shifts from standard photometry to incredibly advanced high-resolution spectroscopy. The researchers utilized the W.M. Keck Observatory in Hawaii.
Okay.
Specifically, they leveraged an instrument called the Keck Planet Finder. And they didn't just measure the star's total light output. They employed astroseismology.
Astroseismology.
Yes, they studied the internal acoustic waves of the star itself.
What's fascinating here is that we tend to think of stars as these silent, static, glowing orbs.
They do, yeah.
But internally, a solar-type star is a violently turbulent environment.
It's chaotic.
In the outer envelope of a star like HR 7672, you have massive convection zones. Huge plumes of superheated plasma are constantly boiling to the surface, cooling and sinking back down.
Mm-hmm.
And this violent, continuous churning generates broadband acoustic noise.
It is an environment of unimaginable acoustic energy. I mean, the turbulence in the convective envelope continuously excites millions of different sound waves.
Sound waves in a star.
Yeah, these are pressure waves, or P modes. And because the star is a bounded sphere of dense plasma, it acts as a three-dimensional resonant cavity.
So the star literally rings like a bell.
It literally does.
The physics of this are just incredible. These acoustic waves travel downward from the surface into the dense interior of the star.
Right.
But the speed of sound in a plasma depends heavily on the temperature and the mean molecular weight of that plasma, right?
Yes, those are the key variables.
So as the sound waves dive deeper toward the core, the temperature and density increase dramatically, which causes the sound waves to refract. They curve back upward toward the surface.
And when those refracted sound waves hit the surface of the star from the inside, they cause the star's outer layers to physically expand and contract.
Wow.
The entire star is constantly pulsating, driven by this internal acoustic resonance. But the crucial part of astroseismology, the mechanism that actually allows us to date the star, lies in how that internal sound speed changes over time.
Right, because the core composition of the star is not static.
Exactly.
As the star ages, it fuses hydrogen into helium.
And helium is denser and heavier than hydrogen.
Okay.
So as the star burns through its main sequence life, helium ash slowly accumulates in the core.
That makes sense.
This gradually increases the mean molecular weight of the star's interior. And because the speed of sound is inversely proportional to the square root of the mean molecular weight, the buildup of helium physically alters the sound speed profile of the entire star.
I see. So as the star ages, the internal acoustic cavity changes its properties, which means the specific frequencies at which the star resonates the pitch of the starquakes shifts over time.
You've got it. By meticulously measuring the frequencies of those surface pulsations, astrophysicists can essentially perform an ultrasound on the star.
An ultrasound on a star. That is wild.
It's amazing. They map the internal density profile, they determine exactly how much helium has accumulated in the core, and from that mass fraction of helium ash, they can calculate the star's age with astonishing precision.
But I mean, the scale of this measurement is what truly blows my mind.
It's hard to wrap your head around.
We are talking about acoustic waves, causing a star to expand and contract by a few meters on an object that is millions of kilometers across, located 58 light years away.
Yeah.
How is an instrument on Earth measuring that physical pulsation?
Well, as the surface of the star heaves outward toward Earth and then contracts inward away from Earth, the light emitted from that surface undergoes a microscopic Doppler shift.
Ah, the Doppler effect.
Right. When the surface moves toward us, the light waves are compressed, shifting slightly toward the blue end of the spectrum.
Okay.
And when it moves away, the light stretches, shifting toward the red.
So the Keck Planet Finder isn't taking pictures.
No. Yeah.
It's a high-resolution Echelle spectrograph, breaking the starlight apart and looking for these minuscule rhythmic shifts in the absorption lines.
And the precision required is just staggering. We are looking for radial velocity shifts on the order of centimeters per second.
Centimeters per second. That's barely a walking pace.
It's incredibly slow. The Keck Planet Finder uses advanced technology like laser frequency combs to create an absolute calibration grid.
Okay.
This ensures that any shift they measure is genuinely coming from the star and not from microscopic temperature fluctuations in the instrument itself. They are measuring variations in the starlight occurring on timescales of mere minutes.
It's like trying to measure the ripples in a cup of coffee from a mile away by watching how the glare of the sun bounces off the surface of the liquid while staring through the turbulent atmosphere of the Earth.
That is a very accurate, if slightly terrifying way to describe the engineering challenge, yes.
It's bordering on magic.
But they did it.
They isolated the acoustic modes of HR 7672, they mapped the helium density of the core, and they derived a precise independent age.
They did. The astroseismic data confirmed that the HR 7672 system is exactly 2.3 billion years old.
2.3 billion years, which instantly assigns that exact same age to the brown dwarf companion.
Boom. Mystery solved.
They finally bypassed the degeneracy problem and forced a brown dwarf to hand over its birth certificate.
Yes, they finally got the timestamp.
But I want to explore why the astrophysics community views this specific system as such a massive breakthrough.
Okay, let's get into it.
Because surely we have found other brown dwarfs orbiting stars before. Why does this one change the game?
Well, while we have detected other brown dwarfs in binary systems, the specific orbital architecture of HR 7672 is exceedingly rare.
Oh, so?
This brown dwarf is orbiting relatively close to its host star.
Okay.
When you analyze the statistical distribution of substellar companions orbiting solar-type stars at these close to intermediate distances, we're talking roughly within 5 astronomical units, you find a glaring statistical anomaly.
What kind of anomaly?
Astrophysicists call it the brown dwarf desert.
A desert, a zone where these objects simply do not exist. We find terrestrial planets close to stars. We find gas giants like Jupiter slightly further out. But in that specific mass range of 13 to 80 Jupiter masses, the data suddenly drops off a cliff.
It is a profound accents, and it points to the fundamental mechanics of how different objects form in a protoplanetary disk.
How do they form?
Well, planets form through core accretion. Dust grains stick together, form pebbles, then planetesimals, and eventually, if a rocky core gets massive enough, it rapidly sweeps up surrounding gas to become a giant planet.
Like Jupiter.
Right. But that process seems to hit a hard upper limit well below the mass of a brown dwarf.
Because by the time a core could accrete 40 or 50 Jupiter masses of gas, the primordial disk has either dissipated or the growing planet has carved such a massive gap in the disk that it starves itself of further material.
Precisely, you just run out of raw material. Brown dwarfs, on the other hand, likely form through the same mechanism as stars, the rapid gravitational fragmentation and collapse of a molecular cloud.
So they form like stars.
Yes. But forming a star and a brown dwarf simultaneously, in such close proximity, creates an incredibly unstable dynamic environment.
Oh, I could imagine.
In most cases, the complex multi-body gravitational interactions during the formation phase either eject the lighter brown dwarf out of the system entirely or force it to spiral inward and merge with the primary star.
So the environment is just too violent for the brown dwarf to survive in that orbit?
Yes.
So finding the HR 7672 brown dwarf sitting perfectly intact right in the middle of this desert is an extreme anomaly.
It's incredibly lucky. It survived the chaotic formation process.
And its survival in that specific orbit is what makes it scientifically invaluable.
Exactly. When theorists attempt to test complex physics models like the atmospheric evolution of substellar objects over billions of years, they require the cleanest possible empirical data.
Makes sense.
If you observe a brown dwarf in a dense young star cluster, its evolution is constantly altered by the intense ultraviolet radiation of nearby massive stars or by chaotic gravitational encounters.
Right. Or if you observe a brown dwarf in a very wide binary orbit, the orbital dynamics are so loose that galactic tidal forces or passing stars could disrupt the system.
Exactly. It's too noisy.
So HR 7672 is a tightly bound, dynamically stable system.
Yes. The brown dwarf is isolated from external galactic perturbations, yet it is far enough from the primary star that it isn't being completely irradiated or tidally shredded.
It exists in a state of pristine, undisturbed evolution.
It is a perfectly clean laboratory.
It is the ultimate control group.
It really is.
It's like trying to test the long-term metabolic effects of a specific nutritional regimen on someone.
Okay, I like this analogy.
If your test subject lives next to a noisy airport, suffers from chronic stress, and occasionally binges at a buffet, any metabolic data you extract is heavily contaminated by external variables.
You wouldn't know what caused what.
Right. You need a subject in a perfectly controlled, isolated bubble where the only variable driving change is the internal biology itself.
The isolation of HR 7672 provides that exact bubble because the environment is chemically and dynamically clean and because we now possess a high... Literally. And then you transition down to the cooler T-type dwarfs, where methane dominates the spectrum and the silicate clouds sink below the visible photosphere.
And theorists have spent decades writing incredibly dense computational models to simulate these phase transitions.
They've had to, yeah.
They've built equations to predict exactly how the opacity of those iron and silicate clouds traps heat, how convection dredges up methane from the interior, and how the luminosity should decline over time.
But without an independently dated object, those models were fundamentally uncalibrated.
Right, because you don't know the starting point.
Theorists would predict that a brown dwarf of a certain mass at 2.3 billion years should exhibit a specific atmospheric chemistry, a specific temperature, and a specific luminosity. But it was entirely theoretical.
Until now.
Until now.
With the HR 7672 brown dwarf, astrophysicists can perform the ultimate mechanical calibration. They take the theoretical evolutionary track, what the physics models predict a 2.3 billion-year-old brown dwarf should look like, and they compare it directly against the physical reality of the HR 7672 observations.
They execute a direct comparison of the empirical bolometric luminosity and the measured effective temperature against the isochrones generated by the models.
And this is the definition of establishing a benchmark object.
Exactly. This is the benchmark.
So let me pose a scenario regarding that benchmark, just to play devil's advocate.
Sure.
What happens if the decades of theoretical modeling turn out to be significantly misaligned with the empirical data?
Okay.
Let's say the observed luminosity of the HR 7672 dwarf is notably higher or lower than what the models predicted for a 2.3 billion-year-old object. Does that invalidate the entire field of substellar physics?
No. It doesn't invalidate the field, it actually accelerates it.
How so?
Discrepancies between theory and a pristine benchmark are exactly how science progresses. If the empirical luminosity deviates from the model, it reveals that our understanding of the underlying physics is incomplete. Ah, I see.
Perhaps the models miscalculated the grain size of the silicate dust in the upper atmosphere, which would alter the opacity and allow heat to escape faster than predicted.
Right.
Or perhaps the internal equation of state governing the electron degeneracy requires some refinement.
The single anchor point forces the theory to evolve to match reality.
Exactly. You iteratively adjust the physics in the model, the opacities, the chemical equilibrium equations, the convective boundary conditions, until the model successfully reproduces the exact temperature and luminosity of the HR 7672 dwarf at 2.3 billion years.
Okay.
Once your model accurately predicts this benchmark, you have successfully calibrated your computational tools.
And once the tool is calibrated, you can turn it toward the rest of the galaxy.
Yes.
You can point your telescope at an isolated brown dwarf floating alone in interstellar space, one that doesn't have a convenient primary star to date it back. take its temperature, run it through the calibrated model, and finally extract a reliable age and mass.
You've got it. We have broken the mass-age luminosity degeneracy.
That is incredible. If we connect this to the bigger picture, the calibration achieved with HR 7672 is really emblematic of a massive paradigm shift in modern astronomy.
Right.
For much of its history, astronomy was an observational science focused primarily on discovery and cataloging. Building larger apertures to capture fainter light, mapping the astrometry, classifying the spectral types.
It was essentially cosmic stamp collecting. We were just trying to figure out what was out there in the dark.
That's a good way to describe it. But discovery is no longer the sole frontier. The current era is defined by precision characterization.
Precision characterization.
Yes, we are no longer satisfied with simply identifying the presence of a celestial body. The science demands that we extract deep, rigorous physical metrics from the faintest possible signals.
We want to know how it ticks.
Exactly. We want to know the internal structural density, the precise chemical abundances, the atmospheric fluid dynamics, and most importantly, the exact evolutionary timeline.
Which is exactly what astroseismology delivers. We're moving from taking static, two-dimensional pictures of the sky to executing complex, three-dimensional physical analyses of objects tens of light years away.
Yes.
And we're doing it using microscopic Doppler shifts in their light.
It's a huge leap forward.
And this specific calibration tool doesn't just apply to brown dwarfs, right?
No.
The ability to precisely date host stars ripples outward across all of planetary science.
Oh, absolutely. It dramatically impacts our study of exoplanets.
Like the ones found by Kepler and TESS.
Yes. Through missions like Kepler and TESS, we have discovered thousands of exoplanets orbiting other stars.
Thousands of them.
Thousands. We know their orbital periods, their radii, and sometimes their masses, but we rarely know their ages with any meaningful precision.
Because if you don't know the age of the host star, you don't know the age of the planetary system.
Exactly. We know they exist, but we don't know where they are in their evolutionary life cycle.
And understanding the age of a planetary system is critical to understanding planetary physics.
Without a doubt. If we observe a gas giant exoplanet that is highly inflated, or a terrestrial planet that appears to have lost its primary atmosphere, we need to know the timeline.
Right, because if it just formed yesterday, that tells you something very different than if it's been around for 10 billion years.
Exactly. Does a terrestrial planet lose its hydrogen envelope to stellar windshipping in 50 million years or 500 million years?
Big difference.
Huge difference. By applying astroseismology to the host stars of exoplanetary systems, listening to the internal acoustic resonance, and mapping the core helium accumulation, we can establish precise ages for the planets orbiting them.
We can start to build an empirical, chronological timeline of planetary evolution across the entire Milky Way.
We can track how planetary orbits migrate over billions of years, how atmospheric chemistry evolves, and how the internal cooling of a planet drives its geological activity.
We are basically transitioning from estimating these processes based on broad assumptions to testing them rigorously against precise empirical temporal benchmarks. So what does this all mean for the future of astrophysics? It means we are systematically removing the fuzziness from the universe.
I like that, removing the fuzziness.
We are taking the vast, complex physics of how celestial bodies form, how they ignite, how they fail, and how they cool down, and we are anchoring all of it to undeniably measurable physical reality.
We are replacing estimated evolutionary tracks with calibrated cosmic time.
Yes.
And that clarification allows us to understand not just isolated anomalous objects like a brown dwarf in a desert, but how entire stellar and planetary systems evolve as interconnected dynamic units over the entire lifespan of the universe.
It puts the timeline back into the cosmos.
It really does.
Which brings us full circle. Space isn't a flat projection.
No, it's not.
It isn't a static photograph where everything just exists in an unchanging present. Time is the hidden dimension that drives every single physical process we observe.
This raises an important question about how we fundamentally perceive the night sky.
Yeah.
For centuries, our observational limits forced us to treat the stars as fixed, unchanging points of light. We analyzed their light devoid of temporal context.
Because we had no other choice.
Right. But by capturing the acoustic resonance of HR 7672 and establishing a precise 2.3 billion year timestamp on its substellar companion, we are learning how to read the dynamic history of the universe.
We're mapping the shifts in the landscape.
Yes.
We finally figured out how to dig down into the starlight and uncover the geological layers of the sky. We found the 2.3 billion year mark hidden in the rhythmic pulsations of a star.
It's profound.
It is. And it leaves me with this one lingering, highly provocative thought for you to just mull over. If taking our modern spectrographs and measuring microscopic, minute-long Doppler shifts in a star's light can reveal the exact multi-billion-year age of a completely different object millions of miles away.
Yeah.
What other invisible ancient physical stories are currently hidden in the subtle, chaotic flickers of the stars we casually look up at every single night?
There's so much left to find.
The sky is no longer a static painting. It's an impossibly complex clock ticking in the dark, and we are finally learning how to read the dial.